Today we'll start looking at vectors. What is a vector? What are some basic properties of vectors? I put together a couple of PowerPoint slides and then we'll fill in the rest of the lecture notes from there. I will put the PowerPoint slides up on Canvas so that you can see what it is that I have here on the screen. First of all, a vector has magnitude and direction. We're talking about vectors in Rn. This is the notation up here for the set of all real numbers, and n is how many dimensions you're in. So if you're in R1, then you're talking about one space. If you're talking about R2, you've got sets of ordered pairs. If you're in R3, you've got sets of ordered triples, and so forth. So if you're in Rn, then a vector in Rn would just have components of x sub 1, x sub 2, x sub 3, until you got to x sub n. So if you're in R22, why would you want to be? You might be. Then you would have 22 tuples, and they would look like that. So a vector has both magnitude and direction. You might look at it like this and think that that's a ray, like from back in high school geometry where it went on forever in one direction. But a vector doesn't go on forever. That vector is exactly as long as that vector that I drew. It's got an initial point, it's called the tail, and then it's got a terminal point, which is called the head. So that's the head, and that's the tail. So the side with the arrow is called the head. The other side is called the tail. If you're starting the vector at the origin, then you write it with components like this. If you have the vector 4, 5, that means that your vector goes in a direction that would be equal to walking 4 units to the right and 5 units up, starting at the origin. They can represent anything. They can represent distance. Oftentimes they do. They can represent force. They can represent other things as well, and you'll see that as we go on through the chapter. The way you name a vector is either with an arrow on top. So if I'm writing on here, I'm going to try to write them with arrows on top because I don't have a bold key on my pen. If you're typing or you're looking at vectors in a textbook, then oftentimes they'll just be a bold. That will tell you the difference, by the way, between a vector not at the origin. So if you have a vector that goes over 4 and up 5 and doesn't start at the origin, oftentimes those vectors will be written like that. And writing it like this will help you to tell the difference between an ordered pair and a vector. Now, the magnitude of its vector is its length. Sometimes you'll write it with the double bars. Sometimes you'll see books that write it with just the one bar. I think our Calc 3 and our linear algebra books actually do them differently from each other. After a while, I just get used to writing it with one single bar. All right, you can also name a vector by its endpoints. So if you have a vector with endpoints p and q, you could write the vector like this, pq. There it is. All right, no fancy things on top of it. If you want the magnitude of PQ, then just put the double bars around it, and you'll have the magnitude of PQ. So the magnitude of a vector should look very much like the Pythagorean theorem. If you have a vector AB, then what you're saying is you're going A units to the right and B units up. Well, how do you find the magnitude of that vector? It's just going to be the square root of a squared plus b squared. If your vector is not in R2, if your vector is in R3 or R4 or Rn, then it's just going to be the square root of the first term squared plus the second term squared plus the third term squared and so forth. All right, when you add vectors, it's important to know that when you add vectors, you add them head to tail. So you wouldn't have two arrows together that you're adding. When you add them, the sum is called the resultant. It's the result of adding the vectors together. So the sum of these two vectors, let's call vector u, u1, u2, let's call vector v, v1, v2. You add them piece by piece. So first component plus first component, second component plus second component. When you do that, you notice that it goes head to tail. So the arrow of one vector touches the point on the other vector. When you add vector u plus vector v, what's the result of adding those two vectors? That's the blue vector that's over here. This is the resultant. This is the sum of adding vector u plus vector v. Right, how would you represent it number-wise? You would represent it this way. You would add the numbers together, and the result of adding those two vectors would be another vector. All right, so take a look at this. We've got two vectors that start at the origin. One vector is the vector 3, 5. The other vector is the vector negative 7, 2. Right, what if I add them together? Well, I could just numerically take them and add them together. 3 plus negative 7 would be the first coordinate. 5 plus 2 would be the second coordinate. I would want to simplify, so I'll get negative 4, 7. All right, what do the vectors look like if I graph them? Well, let's try to make a little graph over here. The first vector, 3, 5, goes 3 to the right, 5 up. Kind of like that. The second vector goes 7 to the left and 2 up. So kind of like that. The result of adding those two vectors together is a vector that goes 4 to the left and 7 up. Right? So that resultant vector would look like this. If you wanted to, you could take this vector over here and slide it over along the second vector, and you would get a vector like this. Right? So you can move this vector over, and now it's head to tail, and that blue vector there is the resultant, is the result of adding those two vectors together. Okay? You could also take this vector on the bottom here and slide it up until you had something that looked like this, and notice that that blue vector, that resultant, is still the third side of the triangle. So that rule still holds no matter which vector I slide. All right, scalar multiplication. A scalar is a constant of some sort. So when you multiply a vector by a constant, it either changes the length of the vector, reverses its direction, or both. So if you multiply a vector by a scalar, you drop that scalar into the first term and the second term. Let's say I had some vector 3, 5. Right? So my vector v is 3, 5. I have a scalar of 3. So if I take that scalar of 3 and multiply it by the vector 3, 5, 3 times 3 is 9. 3 times 5 is 15. So I end up with a vector that's 3 times as long as the original one. If I multiplied it by negative 3, then what I would do is I would make not only a longer vector, but I would make one that goes in the other direction. So instead of a vector that went over 3 up 5 like this, I would end up with a vector that went 9 to the left and 15 down. It would be a vector 3 times as long, but now it goes that way. So if you multiply by a negative, it changes the direction. It flips it 180 degrees. If you multiply by something that's less than 1, it makes the vector shorter. Bigger than 1 makes it bigger. Less than 1 makes it shorter. Right, it's also possible to represent vectors as scalar components in terms of i's and j's. If you haven't seen it before, I is the unit vector 1, 0. It's a vector that goes 1 unit in the x direction. J is the unit vector 0, 1 that goes 1 unit in the y direction, or in the j direction. So if you had a vector, let's say 5, negative 3, that does what? It goes 5 in the x direction, or in the I direction, and then goes 3 down in the j direction. So you could write your vector v as a linear combination of I and j. So it's a linear combination of unit vectors 1, 0 and 0, 1. The first component is called the horizontal component. It tells you how far left and right you're going. This thing here is the vertical component. It tells you how far up and down you're going. When you write them in terms of i's and j's, you're really writing them as what we call a linear combination of I and j. The magnitude is the same thing that we did before, right? It's the square root of a squared plus b squared, and where your a's and your b's, there's your a, there's your b. Just remember, when you square a negative, you get a positive, little things like that. Right, vectors in 3 dimensions work in the same way that vectors in R2 work. So let's try to write a couple of linear combinations over here. Suppose I've got this vector, u, in R3 as 3, negative 4, 2. And vector v is 2, 1, negative 5. Suppose I want to find u plus 2v. Right? What is that? That's the vector 3, negative 4, 2 added to 4, 2, negative 10. All right, so I'm going to double all the components in there. And what do I get? Add your first terms. 3 plus 4 is 7. Add negative 4 plus 2, and you get negative 2. 2 minus 10, negative 8. That is the vector that represents u plus 2v for the vectors that I gave you at the beginning up there. Right, so what are some properties of vector addition and scalar multiplication? And you're going to see these come up again when we talk about vector spaces. The textbook has all 10 of them. They're 10 important properties. I'm just going to kind of zip through them. So properties of vector addition and scalar multiplication. First of all, closure. That's an important one. And what that means is if you add two vectors in, let's say, R3, you're going to get another vector in R3. So closure is important. Notice that in this example I just did, I added two vectors in R3. The answer then was also a vector in R3. That's what closure is. If you perform some operation, the answer comes from the same set that you did, that you have. If you add two integers together, the answer is going to be another integer. So therefore, integers are closed under addition. They're not closed under every operation, but they're closed under addition. The commutative property works. If I add two vectors, it doesn't matter what order I add them in. If I have 3, 5, and 2, 4, it doesn't matter whether I put the 2, 4 first or the 2, 4 second. Under addition, it's the same thing. There's an additive identity, right? There's a 0 vector. So it depends on what value you're in. If you're in R3, for example, the 0 vector is 0, 0, 0. If you're in R4, it's 0, 0, 0, 0, etc. Associative properties work. So if you have three vectors that you're adding together, you can add the first two and then add the third. You can take the second two and then add the first. It doesn't matter. There is an additive inverse. And the additive inverse is just the opposite. So if I add 3, 5 to the additive inverse, which is 3, negative 5, it will produce the 0 vector. So here, I'm taking basically vector u, and then there exists the additive inverse of u that gives me the 0 vector. All right, there is such a thing as closure under scalar multiplication. So this was closure under addition. There is also closure under scalar multiplication. Meaning what? Meaning if I take a scalar times a vector, then that is also a vector in Rn. So if you took a scalar times 3, 5, you would get another vector that's also in R2. Okay, you wouldn't get a vector in R3 or anything like that. The distributive property holds if you take a scalar, and I just kind of jump ahead a little bit. If you take a scalar times a vector, you'll do the scalar times each of the components in there. If you take a scalar times the sum of two vectors, right, you could do that too. You could take a scalar times vector u plus vector v. That'll give you the scalar times the first vector plus the scalar times the second vector, and that's distributive. All right, there's distributive for scalars. So if you have two scalars that are being added together and multiplied by a vector, you can either add the scalars together first and then multiply them by the vector, or you can multiply the scalar times the first and then the second scalar times the same vector, add them together. There's also an associative property for scalars, not for vectors, for scalars. So if you have a scalar times a vector, you could do it that way, right? You could multiply that second scalar by the vector first, then multiply it by the first scalar, or multiply the two scalars together and then multiply it by the vector. And there is also a multiplicative identity. And that multiplicative identity is the scalar 1. So if you take 1 times a vector, you'll get back that same vector. All right, so those are 10 properties that deal with addition and scalar multiplication. You will see much more of that when we start getting into vector spaces very soon. It turns out there's a couple of other things that are true. First of all, the additive inverse of a vector is unique. So if I have two vectors u and v, if vector u plus vector v is equal to 0, then that implies that vector v must be the opposite of vector u, right? They're additive inverses of each other. The additive identity is unique. So if I have vector u plus vector v is equal to 0, then that must mean, not 0. If vector u plus vector v equals v, then that implies that vector u is a 0 vector. Right? That's the additive identity. You can multiply vectors by scalars, so you can take a scalar times a vector, and you'll get, in this case, 0 times a vector, you'll get the 0 matrix. All right, here's where all this is going. You can write a vector as a linear combination. So this is a sort of a fundamental point of what you're going to study in this chapter, is that you can write a vector as a linear combination of other vectors. And here's what it looks like. This vector, vector x, equals c1v1 plus c2v2 plus c3v3 all the way till I get to cnvn. Now, what are these things? The c sub n's are scalars. So c sub 1, c sub 2, c sub 3, c sub n, those are just numbers. The other pieces, the v's, are vectors. So vector 1, vector 2, vector 3, all the way till I get to vector n, and x is a vector also. Let's see if we can try this to see if it's possible, and if so, what are those scalars? For example, suppose I've got vector x equals 2, 6, 14. And then I've got three vectors. Vector 1 is 1, 4, 3. Vector 2 is 3, 5, negative 2. And vector 3 is 1, 1, 2. Okay, so I've got a vector and I've got three other vectors, and I would like to write the vector on the left as a linear combination of the vectors on the right. So let's try this. If this works, and it doesn't always work, but if it does work, then this will be true. Multiplying c sub 1 times 1, 4, 3 plus c sub 2 times 3, 5, negative 2 plus c sub 3 times 1, 1, 2 will give me 2, 6, 14. All right. So how will this work? Well, start expanding things out. C1 times 1 plus C2 times 3 plus C3 times 1 equals 2. So notice I'm taking first component, first component, first component equals first component over there. All right, let's do it for the second components. So I get a 4c sub 1 plus 5c sub 2 plus 1c sub 3 is equal to 6. And now I took second component, second component, second component equals second component. Let's do it again for the third components. 3c sub 1 minus 2c sub 2 plus 2c sub 3 equals 14. And all of a sudden, I've got myself a system of three equations. Let's try to solve this. I'll bet you a matrix is coming in our future. Set up our coefficient matrix, 1, 3, 1, 4, 5, 1, 3, negative 2, 2. And actually, let's make this an augmented matrix. So I will put on the other side of my matrix the 2, 6, 14. And now I've got myself an augmented matrix. Let's try row reducing this. If I can row reduce this, I can solve for those c sub n's, because you notice that everything in that first column is c sub 1 coefficients. Everything in the second column is c sub 2 coefficients. Everything in the third column is the c sub 3 coefficients, and these are the b sub n's. The other thing is, if I move this down for a second, you notice that those vectors, 1, 4, 3, 3, 5, negative 2, and so forth, 1, 4, 3 is now the first column here. 3, 5, negative 2, 1, 1, 2. So if you want to save yourself some time, you can just drop those vectors down the columns of a matrix, and then that fourth vector, that 2, 6, 14, also goes down the column of a matrix. All right, let's see if I can row reduce this rather efficiently. Let's get rid of that 4 and rid of that 3. Let's see if I can do this at the same time. If I take negative 4 row 1 plus row 2, answer goes in row 2. Let's take negative 3 row 1 plus row 3, answer goes in row 3. So my new matrix will start off with a 1, 3, 1, 2. If I multiply that top row by negative 4, I get negative 4, negative 12, negative 4, negative 8. Add these two guys together. What do I get? I get a 0, negative 7, negative 3, negative 2. All right, now take negative 3 times row 1. So negative 3, negative 9, negative 3, negative 6. All right, add these two things together. That gives me 0, negative 11, negative 1, 8. Okay, now what? Now I think I'm going to have to take a combination of these two to get rid of the negative 11 that's down the bottom. Let's do 11 times row 2 plus negative 7 times row 3. Answer goes in row 3. All right, so when I do that here, let me come along the side because these numbers are going to get big. I'll get 0, negative 77, negative 33, negative 22. Down the bottom, I'll still get a 0. Negative 7 times negative 11 is 77. Negative 7 times negative 1 is positive 7. Negative 7 times 8 is negative 56. Add these together, this is my new row 3. 0, 0, negative 26, negative 78. All right, we're getting there. My next matrix then will give me 1, 3, 1, 2, 0, negative 7, negative 3, negative 2, 0, 0. What do you notice about this negative 26 and this negative 78? Can I divide both of these by, I'm getting ahead of myself. Divide both of these by negative 26? I can, because I realize that one is 3 times the other. So divide them by negative 26, and you'll end up with a 1 and a 3. All right, now I'd like to get rid of the 3 and the 1 that's up there. I will eventually get to doing something with that negative 7, but I'd like to hold off on it for a second because otherwise I'm going to create a bunch of messy fractions. So what if I took row 1 minus row 3, answer goes in row 1, and then if I took 3 row 1 plus row 2, answer goes in row 2. All right, let's try that. This time, row 3 is what remains the same. So I get 0, 0, 1, 3. All right, the first row is easy. If I'm doing row 1 minus row 3, 1 minus 0 is 1, 3 minus 0 is 3, 1 minus 1 is 0, 2 minus 3 is negative 1. For the second one, I have to do 3 times row 1, add it to row 2. So now, because now we're going to end up back where we started. Let's scratch that. Let's work with the zeros that are on the bottom. Let's do 3 times row 3 plus row 2. Answer goes in row 2. So I'm leaving this in here. I mean, this is a video, right? I could edit this out. But I think it's good to see sort of a thought process, and that even after you've been doing this for a while, every once in a while you go, uh-oh, what did I just make a mess on here? So this is 0, that's 0, that's 3, and that's 9. So now if I add this to this, and the answer goes in row 2, what do I get? I get 0, I get negative 7, I get 0, and then 9 minus 2 is 7. Okay. I was hoping this would happen. That's why I left that as 7 in the middle, because now you realize that I can just go like this, divide the middle row by -1, and I get 1, 3, 0, -1, 0, 1, 0, -1, 0, 0, 1, 3, and I am almost done. The only thing I have left to do is get rid of that 3 that's up on the top. So let's take -3 times row 2 plus row 1. Answer goes in row 1. All right, so -3 times row 2 will be 0, -3, 0, +3. Bottom row stays the same, 0, 0, 1, 3. Middle row stays the same, 0, 1, 0, -1. And then this 1 plus 0 is 1. 3 minus 3 is 0. That's 0. 3 minus 1 is 2. All right, so my claim is then C sub 1 is 2. C sub 2 is -1. C sub 3 is equal to 3. Does this work? Now, let's find out. The original vectors were 1, 4, 3, 3, 5, -2, and 1, 1, 2. I'm claiming that if you multiply the first vector by 2, the second vector by -1, and the third vector by 3, that will give you the vector on the other side, which was 2, 6, 14. All right, try and see if it works. 2 times 1 is 2, minus 3 is -1, -1 plus 3 is 2. That works. 2 times 4 is 8, 8 minus 5 is 3, plus 3 is 6. That works, and the third one will work also. So you can also write your answer like this. You can write it as 2 vector 1 minus vector 2 plus 3 times vector 3 equals vector x. Okay, so you can write it like that as well, as a linear combination of the vectors. If you were to try to do this row reduction and you got to some point on the bottom, right? So if you did the row reduction and you came all the way down the bottom and you came up with something that didn't make sense, like a row of zeros on the inside and a 1 on the outside, what that means is that there's no solution. And that means that you can't write them as a linear combination. So these things can't be written as a linear combination. Sometimes it's important that it can't be written as a linear combination, and we'll get into that more as the chapter goes on. This video is already getting very long, but that's what it means. So it is possible that you get no solution, and in that case, it just means that it cannot be written as a linear combination of other vectors. All right, we'll take a look at vector spaces in the next video.